Hi. Okay, it's time to get to that problem that I know you've been waiting for. How to do a physics problem of Newton's laws with a block on an incline. So let's get right to it. Let's see. So let's say that we have a block that's on an incline. Just like this. And now that, I think I made that a little steep. Let's just do this. Make it a little less dramatic. There we go. So you have a block on an incline. And let's add friction. Let's live on the edge today. Okay, and the incline is at some angle theta. Okay? So the problem might ask, what is the acceleration of the block as it goes down the incline? So, guess what? The 5 steps. Step 1, choose a coordinate system. Now for this type of problem, it would be simpler to choose a coordinate system that is actually tilted at the same angle as the incline. So, and you'll see why in just a second. So we'll draw a Cartesian coordinate system and we'll tilt it along with the incline. Step 2, identify your forces. So we know that there's a normal force because there is a force of the incline pressing up on the block. We know that the block will want to slide down the incline, so that means the friction would actually be up the incline. So we know there's a force of friction. And just so that I mention it, I realize that different physics books and different teachers have a different style of writing certain symbols. If you'll notice that my friction is a lowercase cursive f. Sometimes you might have a professor that just writes it as friction with a lowercase, meaning friction. Or, sometimes they'll just say a force and they'll put a K, meaning there's a force of kinetic friction, and that's if the friction is on a block that's actually sliding. Or they might put a lowercase s, meaning static friction, meaning it's starting from rest and you're having to find out the force that would be necessary to get it to start moving. But don't get thrown off by the different symbols. They all basically mean friction. You just have to get used to the style of your teacher or your physics book. So we also have to have the force of gravity, and that goes straight down. Now, students sometimes are tempted to write the gravitational force along the y-axis. But what they're doing is they're mixing up 2 different concepts. Since you're accustomed to normally drawing your coordinate system with the x-axis parallel to the horizon, naturally, the gravitational force would be along the y-axis. And they try to superimpose that concept on the axis when you tilt it. But you have to remember that the forces are independent of the coordinate system that you choose. So if the gravitational force is straight down in this coordinate system, it's still going to be straight down in your tilted coordinate system. Okay? So now we've identified all our forces. The one other thing that sometimes throws students is where to draw theta. This sometimes is one of the hardest concepts, but yet the easiest concept to understand. So I'm going to present it in a way that I think is easy. If you see the coordinate system here, you tilt the coordinate system to the same angle theta as the horizon. Well, if the x-axis gets tilted a degree theta, then the y-axis has to get tilted the same degree theta. So as if you looked at the horizon, when you actually tilted the coordinate system, this angle went up from the horizon theta, but this angle went down the horizon theta. Well, the y-axis would rotate over an angle theta, And so would this. So all you had to do is superimpose this angle theta on the y-axis because the y-axis rotates the same angle. If you got a little lost in that, just go ahead, review it, and listen to it again. It's going to sink in. Again, since the incline is an angle theta above the horizontal, then the y-axis would get rotated an angle theta away from the original y-axis, which was straight down, okay? But don't let that throw you. It's really easy, okay? So let's get on with our problem. So we did step 1, we chose a coordinate system. We did step 2, we identified our forces. Step 3, break them into their x and y component. So the sum of the forces in the x direction, if they're going up the incline, they're positive. If they're going down the incline, they're negative. And by the way, you can remember step 1 is choose your coordinate system. You could choose your positive direction to be down the incline, and then your negative direction to be up the incline. You choose. That's the beauty of the problem, your freedom to solve it the way that you feel most comfortable. But for now, I'm just gonna call up the incline the positive direction, okay? So that would be equal to the force of friction minus, now notice, gravity has 2 components. Now you may not see the x component of this gravity initially, so let me help you out. If you look at this relative to this coordinate system, the x component of this vector, and I'm gonna call that mg sub x. That's the x component. And notice that the x component of the vector is parallel to the x-axis. So it's actually this component of the gravity that's pulling the block down the incline. Had you seen that before? Or is this the first time you're actually being able to see it a little better? I hope so. So therefore, we have to find the x component of gravity. So that would be mg sine theta. Now I know what you're thinking, but wait a minute, I thought the x component of a force was going to always be cosine theta. Not necessarily. You get that a lot if you're dealing with a coordinate system that's like this, but that's not the way it always has to be. Let me explain. If you notice, the x component of gravity is side opposite of the right triangle. So therefore, to use the trig function, opposite over hypotenuse is the sine function. So in actuality, it would be mg sine theta to get the x component, not cosine. Don't get locked into using cosine all the time. It doesn't always have to be that way. So are there any other forces moving left or right? No. You might be tempted to say that the normal force is going to the right, but it's not. Not relative to this coordinate system. The normal force is along the y-axis. So we can now say that this is equal to ma. Now, we need the y component of this problem because there's friction. The y component of the force, I mean to say. So now, the normal force is pointing in the positive y direction, minus mg cosine theta equals 0. You see, the y component of gravity is side adjacent to theta. So that's mg sub y. And since side adjacent, the trig function for that is cosine theta, we use cosine theta to get the y component of gravity. Since the block is not falling through the incline or jumping off of it, it has no acceleration along the y-axis. Therefore, the acceleration is equal to 0. So now we can solve for the normal force. The normal force would be equal to mg cosine theta. So we now can substitute that in for our frictional force. So I'll just put a colon here and say that the force of friction, actually I'm substituting for the force of friction, and remember, friction is equal to mu times the normal force, where mu is the coefficient of friction. So we say mu times the normal force, which we're saying is mg cosine theta right here. So we say mg cosine theta minus mg sine theta. We're just writing that over. Fix that little thing I erased there. And that's equal to ma. Well, hey, guess what? That mass, the same mass that's accelerating down the incline, is the same mass that comes from the other part of the equation. So that means we can actually cancel out our masses, and there's our answer. Mu cosine theta minus g sine theta equals A. Now that you have the acceleration of the system, you have your answer. But suppose the problem said, hey, now that you have the acceleration, part B, how long would it take to slide down the incline? Well, that's where you would impose the kinematic equations. But we'll handle that in another exercise.